So the next presenter, it's my pleasure to welcome Professor Cesiulis. He will give his talk about useful techniques, electrochemical impedance, and its application in our project. And yeah, so yes.
Hello, everybody in Portugal. My talk is inspired mainly for one reason. Electrochemical impedance spectroscopy. This function is incorporated installed in almost in each potential stat, galvanostat, and each who work with this equipment see this button and very easily record impedance spectra. And the material selected is inspired by some incorrectness of interpreting of obtained EIS data that I saw in revised papers during discussion with students. So a little bit about this method, just for repeat, but first of all, I would like to express my very special thanks in collection of this material for Natalia Censaro, associate professor, and for three young doctors, Modestas, Edita, and Ramūnas, which we work together. So let's go. What do we know about electrochemical impedance spectroscopy? The electrochemical impedance spectroscopy, everybody know is that this is powerful tool in electrochemical and solid state laboratories. And electrochemical impedance spectroscopy, also called AC impedance or just impedance spectroscopy. And this technique is non-destructive and provide some information about electrical processes and complex interfaces. It is possible to extract some characteristics of materials. The main advantage of this method is a very simple and automatic data recording process. And the main disadvantage of this method is a complex or complicated data analysis for quantification and interpretation. More material about electrochemical impedance spectroscopy and application, and briefly a theory of this method we summarized in this publication. Do you see pointer? Yeah. Okay, so let's go further. Main topics of EIS, I selected 4: AC circuit theory and representation of impedance in complex plane, electrochemical processes and their modeling by passive elements. Passive elements, I mean elements that do not produce electric field like themselves, like resistances, capacitances, or inductive common equivalent circuit models, and extracting model parameters from impedance data. And some data of electrochemical systems recently studied in the framework of our project will be provided. So let's see a few slides I show about basics of electrochemical impedance spectroscopy. This method is based on measuring the response of an electrode to a sinusoidal potential modulation at different frequencies. And all theory of electrochemical impedance spectroscopy is based on Ohm's law, linear dependence between potential and current. However, as you see, the real electrochemical system are not linear, but you can simplify the situation if you select a very small fragment of voltamperogram, and you can use Ohm law at each this fragment, and the fragment usually does not exceed from 2 to 10 millivolts. And so the impedance, like in DC circuits, in AC circuits, can be expressed like also R is resistance, so impedance is also some smart resistance. So also they use this similar relation. However, the exciting potential is changes with time by sinusoidal law, and the response of current also is sinusoidal law. And using Euler relation, it is possible to express the impedance as a complex function. Therefore, you see that this real and imaginary parts of impedance is due to very simple relations, and simplify the whole analysis of impedance data, this Euler's mathematical trick. So it is possible to represent obtained data as this graph, real part, imaginary part, and in some way to interpret this obtained results. So as I see, the interpretation is built up upon a reaction model or equivalent circuit consisting of passive elements. As I said, there is three elements, so impedance of each element is right in this way. So, for example, so you can simply like resistances. So impedance also is if you have in series reactions or in series elements, you can make some in this way. The general impedance of parallel processes is like this. So we don't go far away from Ohm law and Kirchhoff law. Macroscopic impedance, for example, interaction rate distribution. Okay, I don't show you. So you see a semicircle with imaginary parts. I can note you that the responsible for imaginary part is only by capacitances. Only by capacitances and inductances. We will see later on. So the macroscopic impedance is not uniform. And if we have simple electrode processes that consist of double electric layer and charge transfer, so, and solution resistance or or uncompensated resistance. Sometimes the macroscopic reaction rate distribution are distributed across surfaces, and we will see not ideal semicircles, but flattened semicircles. And consequently, in the Nyquist plot, the semicircle is flattened, but the resistance of charge transfer resistance, these violet arrows, might be the same. Usually, electrode processes contains the similar stages regardless their nature, and comprise some similar processes, such as formation of double electric layer, the presence of ohmic resistance or resistance of solution, charge transfer resistance of electrochemical reaction, adsorbate layers formed by intermediates. So, the very different processes, electrode processes, shows the similar impedance response. So like this, you see here is for cathodic deposition, we have such loop. And for, we can found simple systems for anodic dissolution, that also we have similar shape of Nyquist plot. So, so we can use, sometimes we have a few semicircles or a few or semicircle and inductive loop, and we have to make let's say political decision which process I expected be occurring on the electrode, consequent charge transfer or parallel adsorbing or very harmful adsorbate layers like this. But I want to point your attention on diffusion in the electrochemical systems. It is the diffusion impedance is right like this, and here the sigma is a Warburg constant. And as you see, the diffusion impedance is only the only one impedance that can be calculated separately. And you can evaluate the diffusion processes on the list of paper. And sometimes, of course, we see this ideal Nyquist plot for processes including diffusion or Warburg like this. So, but in each time, if I expect a diffusion, I suggest to prove this your decision by separately and ask questions: what particle are diffuses, and it is possible to have the place for this diffusion. So the proving of diffusion, I show briefly one similar one simple system, platinum electrode in a ferriferro solution, ferrocyanide solution. This in this system, the diffusion limitation approved many times, and the impedance spectra is like this ideal spectra, which see some fragment of semicircle because of charge transfer resistance, and because of charge transfer, and big diffusion line, with slope of at 45 degrees. So what represents diffusion? I would like to pay your attention. This is at equilibrium potential. So something like here somewhere. I would like to pay your attention on these values of impedance values. This is a tenth of, in this system is a tenth of ohms. However, so what other potentials also, the Nimbus plots are similar and we see the same picture. However, I would like to pay your attention. What happened when at the electrode, at the surface of electrode, the concentration of ions became close to zero. Impedance close to zero. So you see the variable constant until diffusion impedance goes to infinity. So in this case, if you at this potential, if you if you measure at this potential, so where limiting diffusion current is, so it is, you see big numbers of impedance. That means that you have a real diffusion current. So another case study is cobalt reduction on the electrodes from various solutions. Also, they have some plateau. But you can very similarly to calculate this limiting current densities, and you see that current densities are obtained current densities is much smaller than theoretical diffusion current density. And the impedance at this point, you see the very small impedance data. This is tens of ohms. So it means that this plateau does not correlate with diffusion current, limiting diffusion current. So another application, good application for impedance is analysis of data and prognosis forecast for electrodeposition in membranes. In our case, it was anodized aluminum oxide membranes. So the membrane, you know, this is a very narrow channel, half a channel. Inside channel, the diffusion is planar, and outside channel, because of the size and dimensions, you have a spherical diffusion, and the aim is to in uniform way to fill up this channels. So you can predict let's say pulse current parameters in order to deposit uniformly in these channels. So impedance data in the presence of diffusion have some critical frequency. Here is high frequency, here is a low frequency, and here is some critical where kinetic control transforms into diffusion control. And of course, it is better to work in kinetic control, and in this case, the critical is frequency 0.3 hertz. So really we work on 5 hertz, and we uniformly, as you see here, electron filled this membrane by cobalt tungsten alloy. So another application of electrochemical impedance spectroscopy it is possible to determine a thickness of oxide layers, of intermediate oxide layers, and in our case, this was a study of corrosion of cobalt tungsten alloy. So you see that during corrosion, the diffusion, the impedance spectra are quite complicated. So here you see a equivalent circuit, and based on this data of a capacitance of double electric layer, it is possible using some simple physical equations to calculate the thickness of oxide layer. Of case, we assumed that the electric constant of oxides are equivalent for their molar fractions, and the presence of oxides also were proved by EDS data. So you see that it is the obtained values of thickness dependently on tungsten content, depends on tungsten content, and during electrochemical reactions, the oxide layer is close to monomolecular layer. So another application for electrochemical impedance spectra is analysis of 3D electrodes, and in our case we use copper foam electrodes, and of course the materials with high specific area are very important, and important to determine specific area, and we measured potential and understood that the specific area, the apparent specific area, depends on the processes that you are using. Let's say double electric layer, charge transfer resistance, or mass transfer to the electrode. So if you you see the similar shapes of Nyquist plots, and during analysis of impedance data, we find that the capacitance of double electric layer extracted from impedance data on the flat electrode and on the porous, these green lines, on porous or foam electrode, differs some intense time, about 7 to 15 times. So it means that, of course, the area of foam is higher. However, if you analyze charge transfer resistance. In this case, the difference is not so big. This is red lines. And the difference is not big, about 2 times only. So the working area for charge transfer is just higher, just 2 times. So if we analyze mass transfer, for mass transfer, we use this circuit. This circuit as a combination of constant phase resistance and charge transfer resistance. So we find that diffusion resistance, it is very convenient to use this expression, because you don't you don't use diffusion coefficient, which is a little bit different, differs from solution to solution. So we calculated diffusion potentials, and diffusion potentials is you see for diffusion processes in a form are about 3 times less than on the flat surfaces. That means that diffusion occurs 3 times faster on this electrode. So one more application of this is anodization of tungsten and formation of tungsten oxide in various solutions. The impedance spectra, as you see, is quite complicated, and this impedance spectra, it was possible to describe assuming that we have a few interfaces, is metal and I mean tungsten and tungsten oxide interface, and tungsten oxide and solution interface. And in this case, using this equivalent circuits, we describe this spectra. The points are experimental data, solid lines is fitting parameters, and so you see that this approach is quite good. Moreover, based on double electric layer capacitances, we determined the thickness of obtained layers. So using impedance data, it is possible to calculate from monolayer to up to 10 nanometers size of layer. So also it is possible to determine using Mott-Schottky curves and procedures, determine other properties of obtained semiconductors, and namely to determine, calculate the defect density or potential gaps. So here you see also this data are in line with others methods. So I will finish, and looking forward, the Ramūnas is in our group is biggest expert on intensity modulated photocurrent spectroscopy, but probably he got some words. I would like to finish this slide, my talk, and to summarize, to say that this is a powerful tool, and its applications are developing continuously. We have sensing, impedance sensors. now is very fastly developing trend in electrochemical impedance spectroscopy. So, acknowledgement for our smart electrodes project. All news are on this page. So thank you for attention.
Thank you, Henrikas. Thank you for your presentation and to remind us again about impedance.